Hi guys. So let's discuss this problem called common absolute difference. It's an interesting one. So we are essentially given an array A that contains n integers, and on top of this array we are given an integer k. And what we are asked is we need to count the number of pairs ij such that I less than j. So we have to ensure the pairs are ordered and they follow a condition. Basically, AI minus AJ, the absolute difference between AI minus AJ should be exactly K. So that's the condition. Uh, let's look at the problem statement from a clearer angle, taking an example. Uh, so let's take this example where array is this following 1, 2, 3, 4, 5, and K is given as 2. So so the number of pairs of ij such that I less than j, and this condition being followed. So let's fix a particular I, uh, wherein I equals to 0. All we need to figure out, or rather, my bad. Let's iterate it over j. So when j equal to 0, there are no I before it, so the contribution will be 0. When j will be 1, there is an I before it, but there is no I such that the distance is 2. That is, prior to this element 2, there was neither a 0 nor a 4, right? So the contribution for that element is also 0. But when j comes here to 3, then we can see there is exactly one person which is at a distance of 2 apart. So and the index is I equal to 0. So we contribute 1 for that. So 0, 2 is one pair. And similarly, when j equal to 4, among all the previous elements, only 2 qualifies. The element 2, which is at index 1, qualifies. And hence 1 and 3 is another feasible pair. And when j comes to 5, um, like the, the index at 2, um, for the element 3 qualifies. So therefore 2, 4 is another feasible pair. Okay. And these are the three ordered pairs. Note the word ordered is important here because 2, 0 also satisfies this absolute difference condition, right? The index 2 comma 0, that is 3 comma 1, also satisfies this, but it does not satisfy this criteria of I less than j. When you put 2 here, that essentially puts um, so yeah, so 2, 0, that is 3, 1. Uh, 3, 1 satisfies this criteria, but 2, 0 does not satisfy 2 less than 0 criteria. And similarly, by the same line of argument, 3, 1 and 4, 2 do not qualify, although the distance between them is 2. Um, yeah, so that is one thing to note. It's an ordered pair counting question. Okay. And how can we visually interpret this? Well, absolute difference between these two numbers is essentially visualized can essentially be visualized using a number line. So imagine you are standing at this arbitrary j, and let's say the element at this position is x, that is aj is equal to x. Now, if we take a jump of k in the right, or take a jump of k in the left direction, both of them are potential candidates for AI, right? Um, so so that is fine. So when we are at an arbitrary jth index, all we need to care about is take a jump of k to the right, or take a jump of k to the left, and then tell me for each of these elements that we end up at, what was what how many numbers were there prior to this j that is less than this j. That's what we are asking. Um, so yeah, that's what we will be discussing in this slide. So for a given j, what can be the potential value of ai? Well, aj minus k go to the left direction, aj plus k go to the right direction. And there can be multiple occurrences of each of these aj minus k. There can be multiple I uh, to my left, to my left, to this left of this jth index that can have the same value of aj minus k, right? So that gives us an intuition to use a frequency data structure, like a frequency map or a frequency table or a frequency array, something like that. So for example, if we are standing at this j, at all these indices I1, I2, I3, all of them pertain to this value of aj minus k, right? The element here pertain to aj minus k, aj minus k, so on and so forth. Here also at I3, right? So we need to figure out the frequency of this. So the choice of j will be what? Because we have fixed for this given j, we are asking the question how many I are present. So there is just one choice of j. It can be taken in one way. But what are the choices of I? Well, that is essentially frequency of aj minus k. That will essentially contribute one for each of these. And therefore, we have essentially aggregated all ij such that all the i's are to the left of j and ai is equal to aj minus k. And by the same line of argument, by symmetrical argument, we can say, okay, just change the key and like query for frequency of aj plus k, and that will give me for the key 2, give me the answer for the for key 2. Okay. Um, okay, so putting everything together, there is just one choice, like the j choice is 1, and for key 1, this is the frequency of aj minus k is the number of is the yeah, number of ways to do that, and frequency of aj plus k is the number of ways to pick key 2, right? And so one thing to note here is, had k been 0, we would have over counted here, right? We would have counted both the things twice. That's one thing to note here. So therefore, you will see in the question, k will be greater than, strictly greater than 0. You will, yeah, k starts from 1. And that's how. So this answer is for a fixed value of j. Now to get the answer for the overall question, we just need to aggregate this function for all the values of j, starting from 0 all the way till n minus 1. Okay. Um, and one last question to ask ourselves is, how do we ensure this I is less than j in the frequency map? Well, that is simple. We just iterate from left to right and we populate the array um, then and there. So for this arbitrary j, we have populated a map from left to right. That means the map would not contain any element to the right of j, right? All of the elements in the map will pertain to this range. Uh, that is the left of j indices. And that's how we will ensure whatever the state of the map be at a given value of j, it will only contain values at indices less than j, strictly less than j. And yeah, and after finding out the value for this j, we need to update update the map for future j's. For future j's, this given j might be of importance. So we will update the structure, update the map, and then move on to the next j. Okay. One last question that generally we should ask ourselves for better practice in these counting questions is there any undercounting going on, or is there any overcounting going on? If we like kind of argue this in our head every time, uh, and the arguments need to be strong enough, then it's a better practice to go about solving counting questions. Um, so, for example, in this question, is it undercounting? Whatever aggregation we have done, is it ever undercounting? Well, undercounting happens when there is something left out, right? So imagine all the answer pairs, right? All the answer IJs that have satisfied the criteria. Can you ever imagine a pair where the J is less than 0 or greater than equal to n? It can never happen, right? J will always be within 1 to, 0 to n minus 1, right? 0 to n minus 1. And that's exactly what we are doing here in the previous slide. Um, we have taken j 0 to n minus 1. That means we will never, if at all we have counted the correct answer for each j, there is nothing that is remaining uh, for j, right? We are not leaving out anything. So we are exhausting all the possibilities essentially. So there is no point of undercounting happening there. And by the same line of, yeah, that's the argument that we will that essentially we need to say to answer the undercounting question. For overcounting question, that is, this generally happens, overcounting generally happens when um, something gets added two or more times, right? Greater than equal to two times. And how do we ensure that? Well, the way we are iterating on j, these will always be disjoint, because for a given j in the map, uh, it's every element is contributing exactly one to some frequency of some key, right? And therefore it can never be disjoint, right? The j is fixed, and all these indices, feasible I indices, those are also disjoint, right? In fact, if you take for a particular key as well, that is also disjoint because it was incremented by one at different indices. Okay, that is one. The second argument is for different values of j, uh, for different values of j, the pairs that we will get will at least be disjoint at these two places, j1 and j2, right? So inherently, there won't be anything common between all the pairs that we have generated for this J1 or and for this that J2. There won't be anything common. So that's the argument that we are never double counting anything, right? So so that is a short correctness argument to what we have implemented. And finally, the complexity of this, let's come to this after we discuss the code in short. So the way I have implemented it is I'm iterating over all potential values of j. We have taken a data structure map. This is a balanced binary search tree. And then, yeah, okay. And then I'm also initializing an array. Whatever be the value of aj, I'm making a jump of k to the right, and figuring out the frequency of that. And this is the J choice. It can be chosen in one way. And this is the choice for number of elements on the number line, uh, which are k distance apart. So, and for this particular value of j, just aggregating both of them, essentially, this is what we have already discussed. We need to be careful for j should be greater than equal to 1, right? Although it won't matter in this case, we'll just make MPP value 0. Um, and this is important. We need to update the structure after we have figured out the answer for the jth uh, index, because this potential this value of the array at position j might be a potential candidate for some j in the future, that is to the right of j. So we update the structure, and then finally we just print out the answer. So So now let's come back to time complexity. So for query, that is how many the frequency. Um, First of all, when we are populating, uh, yeah, when we are okay, it's did I populate this? Just a second. Yeah, this is correct. So this is querying. Okay, so we are essentially searching for the frequency for a given key. So that's what we have written here, that querying will overall take log n time, and then insert we are doing at the end for future j's. That will also take order log n because it's a ordered map. And how many times we are doing? Well, the j iterator goes from 0 all the way through n minus 1. So n times. So overall the complexity will be order n log n, and the space complexity will be order n pertaining to the map data structure. So that concludes the solution to this video. Thank you. Thank you for watching.